Okay, well, we're back again. We're doing another derivative problem here. This one is a product of a couple of binomials to a power, specifically f of x equals 3x plus 2 to the 5th power times 4x minus 7 to the 8th power. So if you've already done this one, great. Let's keep going. If not, go ahead and try to work out the first derivative formula for this function before you proceed. Press pause now. Well, it's actually easier to see what's going on if we do a couple of substitutions, which we're going to have to do at least in our head eventually. So 3x plus 2, let's let that be u, and let's let 4x minus 7 be w. And this becomes then the derivative of u to the 5th times w to the 8th. Well, the last thing we do in this evaluating this function is multiply, so we use the multiplication or product rule. So the product rule says it's the first factor times the derivative of the second plus the second factor times the derivative of the first. By the way, the product rule, there are some other orders you might see this written. You might see these two terms reversed here because addition is commutative. You might see these two terms or these two terms reversed because multiplication is commutative as well. I have a tendency to write it this way. I like to write down the stuff that doesn't change first and then the part that we have to focus on the derivative second. And then I just do the first, start with the first one. So this is the way I write it. I like to try to write it the same order every time. So I encourage you to pick an order and do it the same way every time to help reinforce it. But this is the order I choose. So anyway, here we go. The derivative of w to the 8th is 8w to the 7th times the derivative of w. The derivative of u to the 5th is 5u to the 4th times the derivative of u. So we're using the power rule and the chain rule at that point. Now I'm going to rewrite this as 8u to the 5th, w to the 7th. Notice the last step, that u to the 5th and w to the 8th just came down. The plus as well, and the equals, of course. And rewrote this as 8u to the 5th, w to the 7th, and this part we can rewrite as 5u to the 4th, w to the 8th. Now substitute back in, w is 4x minus 7, and u is 3x plus 2. The derivative of 3x plus 2 is just 3. The derivative of 4x minus 7 is just 4. And so now we basically have the derivative here. 4 times 8 is 32. 3 times 5 is 15. And then we want to see if we can factor this out. It's easier to see if we don't do the substitution back yet. We see u's in both of these. So we go with the smaller power, 5 and 4. The smaller power is 4. So we pull out a u to the 4th. We see some w's here. This one has 7. This one has 8. We go with the smaller amount, which is 7 for the power, and bring that out front. 32 is just 2 to the 4th power, 2 to the 5th power, excuse me. So it just only has factors of 2. 15 is 3 times 5. So they have no factors in common. So I'm not going to be able to get anything else out of this. Now substitute back in. I'm going to substitute back in here. I'm going to leave this just floating along for a little bit to save me some writing. So u is 3x plus 2. W is 4x minus 7. I can do some simplification inside this set of parentheses here. So I can distribute to 32. 32 times 3 is 96 times the x there. 32 times 2 is 64. 15 times 4x is 60x. And 15 times negative 7 is negative 105. Combine like terms, 96x plus 60x is 156x, 64 minus 105 is negative 41, and I finally substitute the u and the w. Let's see if I did that right. Yeah, 3x plus 2 for u here, and for w I put 4x minus 7 there. And then you want to factor this out if you can. I believe 41 is prime, and it doesn't divide into 156 evenly, so that's going to be factored all the way. And we really prefer these things factored out because one of the things we want to do oftentimes is find where the original function has a minimum or maximum, okay, or an inflection point. And so the potentials for these are when the first derivative or the second derivative is either 0 or undefined. And so we look at this. If it's factored, we can easily see this and do the algebra that we need in our head here. So this factor is equal to 0 when x is negative 2/3. This factor is 0 when x is positive 7/4. And this factor is 0 when x is 41 over 156. So those are all x values where the original function has a horizontal tangent line, or also known as a stationary point. and those are our potential values for a minimum or maximum of the original function. Okay, let's do a second derivative. Okay, if you haven't done that yet, take this function here and do a second derivative. Let me hint. Try the same substitution here to make it a little bit easier right at the beginning. Okay, if you haven't done this yet, go ahead and do it now. Press pause. Okay, well, let's take a look at this. So the first thing I did is that same substitution, same u and the same w, 3x plus 2 to the 4th, 4x minus 7 to the 7th, 156x minus 41. Wrote it that way. Now, this is the triple product rule, or the more generalized product rule. It says, I'm doing it in a slightly different order here, the way I usually do this. Just take the derivative of the first times the other two, plus the derivative of the second times the other two, plus the derivative of the third times the other two. So this is derivative of u to the 4th. Then we still got times the w to the 7th and the times 156x minus 41. Plus, we have the first and the third factors, that's u to the 4th and 156x minus 41, and then we take the derivative of the middle one, w to the 7th, multiply those together. And the last one, we multiply the first two, and then we just take the derivative of the last part. And all three of those things are added together. So that's the generalized version of the product rule. Now let's see here. The derivative of u to the 4th is 4u cubed times the derivative of the u. And we still got times w7 times 156x minus 41. Here we have the u to the 4th. The derivative of w7th is 7w to the 6th times the derivative of w. And then we still have times the 156x minus 41. Plus, here we have these two, u to the 4th times w to the 7th. And the derivative of 156x minus 41 is just 156. Alright, let's see if we can clean some stuff up here. U is, make sure you got this right, 3x plus 2. Good. And w is 4x minus 7. So that goes in here and here, because those are the parts we have to take the derivative of still. The derivative of 3x plus 2 is 3. The derivative of the 4x minus 7 is 4. Alright, so we're down to this point. We've done all the derivatives. Now we just got to clean it up a bit. So I'm going to do some factoring. If you notice, everything has, first of all, has a 12. There's a 4 and a 3 makes 12 in this one. There's a 4 there. And let's see. Where is the 3 here? I don't see the 3 here. Something's wrong. Oh, I'm sorry. This is not a 12. It's just a 4. What I did is I multiplied these back out, which I didn't necessarily have to do. But maybe it's easier to see this way. 3 times 4 is 12. U cubed and w to the 7th. And then we have this one. Here we have 7 times 4 is 28. Then u to the 4th w to the 6th times this factor here. And 156 u to the 4th w to the 7th. So to kind of get them all in the same way. Now we see they do have a 4 in common. 12. 4 goes into 12 3 times. 4 goes into 28 7 times. 156 divided by 4 is 39. Those all work out evenly, but that's the only thing that we can get out as far as the constants go. Anything else would have to be 3 because of this, and then 7 here, that doesn't match. So we get a 4 out, but nothing bigger. Now we can also get a u and w out to some power. We go with the smallest powers, and the powers on u are 3, 4, and 4, so we go with 3. And for w's, we have power 7, 6, and 7, so we go with 6, the smallest power. Now we divide each thing by 4, u cubed, and w to the 6th. As I said before, 12 divided by 4 is 3. The u's cancel out. W to the 7th divided by w to the 6th is just w, and we still have this other factor of 156x minus 41. Plus, 28 divided by 4 is 7. U to the 4th divided by u cubed is u, and the w's, notice, are the same, so they cancel out. And we still have this factor of 156x minus 41. Finally, 156 divided by 4 is 39. Let's see. That's correct. And then w to the 4th divided by u to the 4th divided by u cubed is a u. W to the 7th divided by w to the 6th is a w. Now I'm just going to leave this out front for a moment. W, let's go back, is 4x minus 7. So that's going to happen right here and right here at the end. And then the U is 3x plus 2. So that's going to go here and here. Alright, now we got a lot of algebra going on. We need to distribute this, multiply it out. So we're using the FOIL property here. We'll leave the 3 here. 4 times 4x times 156x is 624x squared. That's the first times first. Last times last. Negative 7 times negative 41 is positive 287. Then for the inner product, negative 7 times 156x. The outer product is negative 41 times 4x, and that should combine, if I did my arithmetic and algebra right here, that should turn out to be negative 1,256x. You can check me on that. Here we have a 7 here. We FOIL this. 3x times 156x is 468x squared. 2 times negative 41 is negative 82. To get the middle term, it's 2 times 156x. That's 312x minus 41 times 3x. That turns out to be 189x positive. Here we do FOIL here. 3x times 4x is 12x squared. 2 times negative 7 is negative 14. Here we get 8x minus 21x is negative 13x. Now we distribute the 3 here. Multiply each of these 3 by 3. We get these 3 terms. Multiply each of these by 7, we get these 3 terms. And multiply each of these 3 by 39, we get these 3 terms. Okay, you can check that out. And then combine like terms, get the x squares together. There's 3 terms that have x squared together. Add their coefficients. Hopefully if I did that right, that's 5,616 x squares. Then add the x terms together, this one right here, here, and here. And by my calculation, that's negative 2,952x. And then the constants here, here, and here are there. And then we factor that if we can. It doesn't factor, I think it may actually be prime, but it doesn't factor nicely. And then these, substitute back in what U and W are. And there's the second derivative. So that was both of these involved a little bit of work. We did this substitution, and we're doing the product rule, the power rule, and the chain rule. And then we had some maybe not completely insignificant algebra here, where we had to do some substitution. We had to do some expanding here and combining like terms. It gets a little nastier on the second derivative. But same basic idea. We use the generalized product rule to think of it as the product of 3 things and use that to write it out like this. Then we use the power rule and the chain rule a couple places, and then just the derivative of a linear function on the other part. And then I did a lot of algebra, right? A lot of polynomial algebra. Multiplying out with FOIL several times. Some of the numbers got kind of large. Distributing, distributive property, regrouping, combining like terms, which is actually the commutative and associative properties there, distributive property working together to combine like terms, and then we do some factoring there, and we get our final answer there. All right, how about the tangent line? Okay, first of all, we're talking about at x equals 1. Now we could do a tangent line at any place, not just x equals 1, but the directions said, way back when I did the directions, they said do the derivative when x equals 1. So I just plug in x equals 1 in the original function here and here. I believe I have that worked out down here. That's 3 times 1 plus 2 to the 5th, 4 times 1 minus 7 to the 8th. Multiply those 2 things. So 3 times 1 is 3 plus 2 is 5, so that's 5 to the 5th. 4 times 1 is 4 minus 7 is negative 3 to the 8th. 5 to the 5th times negative 3 to the 8th. Yeah, I used a calculator on that part. But you could do that by hand, but it's a lot nicer to do with the calculator. And that's 20,503,125. So that's the y value on that. So if we're going to see this point of tangency, our y scale's got to go up, higher than that. Now, what's the slope there? The slope is also a rather large absolute value. We take the derivative formula, which is this right here, plug in a 1 for all three of the x's. So that's again, we get 5 for this one and -3 for this one. The powers are 4 and 7 this time. And you plug in a 1 here. 1 times 156 minus 41 is 115. Multiply all this out. By the way, notice 7 negatives altogether, so we do need a negative slope. So the function is going to be decreasing at that particular point. And the slope is a negative 157,190,625. Okay, so the tangent line is y equals, or t of x equals, the slope, which is the derivative, this negative 157 million, so forth, times x minus the x value of 1, plus the y value of the original function, which is 20 million something. Now here I graphed it. I had to go pretty far out to see the interesting things. So looks like the original function is f of x, which is blue here. So this one coming up like this. You can follow my cursor. The red one coming down here and then back up and down and back up here. That's the derivative. The green one is the second derivative, and the purple line is the tangent line. So notice when x is 1, right here is where the tangent line and the function touch. I had to go way out on the scale. I'm pretty close in on the x's actually. I'm between, looks like about a negative, let's scale here. Looks like a negative 1.5 to about 2.85 or so on the x's. But if you look, I went way down, down past, it looks like down past negative 2.5 times 10 to the 9th power and up to, looks like around 2 times 10 to the 9th power. So way up there and way down. Okay, now let's see what we can see here. So we know that the point 1 comma 20,503,125 is this point right here where the tangent line and the function cross. If we were to zoom in here a little bit more closely, right in here, we would see the tangent line follows the curve pretty closely there. We would see that the original function crosses the x-axis at negative 2/3 and at positive 7/4. And not only that, this is a multiplicity 5 root. So when we see it there, it's going to be an inflection point and a horizontal tangent line there. Because what happens when we have an odd power here on the 3x plus 2, notice that the derivative has the 3x plus 2 to the 4th power eventually. So the derivative is also 0 there. And if we take another derivative, we're going to end up with 3x plus 2 to the 3rd power in our final answer for our second derivative as one of our factors. So the second derivative is also 0 there. So that was at negative 2/3, negative 0.6 repeating, which is right here. And notice that the derivative, first derivative, second derivative, and the original function are all 0 there. And in this particular case, being an odd power on the original function, it's actually an inflection point in the original, which makes it, in this case, a minimum or maximum, in this case, a minimum on the first derivative, and it's actually an inflection point on the second derivative as well. So that's our multiplicity 5, I think it was, root on the original function. Then we also had a multiplicity 8 root, so it's going to touch and turn around. This is power 8 here, same factor to power 7 in the derivative, same factor to power 6 in the second derivative. And so the first and second derivatives and the original function are all 0. They cross the x-axis at 7/4. That's, what is that, 7/4? That's 1.75. And that's right, 1.75 is right there, actually. And so all three of them cross there. In fact, it's a little hard to see, but that's a multiplicity 8 root. So in fact, we're losing some detail here. but in fact the graph of the original function touches and turns around there. So actually, probably, we'll look at this a little bit more closely, but it's probably touching and then coming back up, which is the same thing that the second derivative does, whereas the third derivative goes on through. So it's horizontal, but it's actually a minimum looks like there for that particular point on the original function. Now let's see if we can look at the graph and see some of the characteristics of the graph. Alright, notice here the original function on this first piece on the far left is increasing, concave down. So the original function must be positive. The first derivative must be positive, which you see is here, is above the axis. But the first derivative is decreasing, and the second derivative is negative, where the original function is concave down. Then right here at negative 2/3, it hits the original function hits the x-axis. It's also an inflection point there, so it continues to increase, but it's now concave up. So now the derivative, it was also 0 there, right at negative 2/3, but then becomes positive after that. So this function is increasing all this time where the derivative is positive, up until this point right here, which by the way is whenever the first derivative is 0, so 41 over 156. So 41 1/56 is this place where the derivative crosses the x-axis. That's going to be the x value of the maximum, local maximum right there on the original function. Alright, so let's continue to look here. Now notice that the original function is increasing, concave up. The second derivative comes down here and touches the x-axis right in here. Well, I don't know exactly what that value is, but I could find it by using the quadratic formula on this quadratic factor, probably some irrational thing, most likely. But if I use my quadratic formula on this and find the roots of this quadratic polynomial, one of them is going to be around negative 0.0 something, okay, and it's going to be right there. And that's going to be where the original function has an inflection point, and the first derivative has a maximum here. Okay, and so from that point on to this point right here, at what was it, 41 over 156, we have the original function is increasing, concave down. So the derivative is positive, but the second derivative is negative. Okay. Now, if it stays concave down all the way over to here, where the first derivative, where the second derivative is 0, that's the other factor, the other x value that makes this quadratic function 0. So that would be a positive root that we would get out of the quadratic formula. And whatever that value is, that's where the derivative has a minimum, and the original function has an inflection point. So in between these two inflection points, concave down, second derivative is negative. Okay, so in between here, the original function's concave down and decreasing. Then it continues to decrease here. Notice that the first derivative is still negative down here, but it's concave up. The original function is concave up and decreasing. The second derivative is positive, and the first derivative is negative. Now, somewhere over here, let's see, so it continues to come down, decreasing, concave up. Notice that the second derivative is positive all the way through here, and the first derivative is negative all the way through here. So that means for this whole piece, the original function is decreasing, concave up, and they all hit the graph each other, and the x-axis all touch at x equals 7/4, and that's right in here, actually right there. And the original function has a minimum there. And then from there on, the original function is increasing, concave up, and in fact, all three of the derivatives, the original function, the first derivative, and the second derivative, they're all positive there, so that, and actually increasing, concave up, all there, as you see from the graph. Okay, that one has a little interesting algebra. It's easy to get lost in that, in working through that algebra, so take it easy. Write everything down. I know a lot of folks, when they do derivatives like this, they do a lot of this stuff in their head. I try to be very, very explicit about writing down exactly what I'm substituting, writing down every gory detail. And on a more complicated problem like this can really save you from making some kind of careless mistake. Of course, it is possible with more practice to get to where you can do more of these things in your head. Okay, so come back in the next video and let's look at this function here, 3 to the x squared times e to the 4x. So if you haven't done that one already, you might try that before you start the next video. Find its first derivative.